Good morning, good afternoon, good evening, depending on which part of the globe you come from. I'm Veda. We have been running this webinar series from the IEEE Census Council in association with IEEE for the last 2 months. This is the fourth webinar in the whole series, and I have two eminent speakers from industry who will be delivering the talk. So we have first talk coming from Dr. Matthias. He is actually from Robert Bosch, based in Germany. He is a senior manager and a senior expert on system architecture. And he's going to take us into the world of inertial sensors. And his talk is basically very interesting, where he's talking about MEMS transforming vehicles and gadgets. So we're going to go into his world of MEMS. And Matthias, thank you for accepting this invitation, and it's all yours.
Thank you very much for the kind introduction. So I will share my screen now. Can you see it?
Yeah, we can. You can go ahead.
Okay, perfect. Thank you very much. So my title is, as said, Transforming Vehicles and Gadgets. And to my person, shortly, I'm a physicist. I graduated in physics and did my PhD there. And right now I'm at Bosch. I'm in the pre-development department of MEMS, and acting there as a senior manager and also a senior expert for MEMS in the realm of system architecture. And I'm very happy for this opportunity to give you a glimpse of what Bosch does in the MEMS industry and also what kind of MEMS we produce in the different fields and applications. So at first, a short introduction into Bosch, into the company, and specifically what we're doing for MEMS. So Bosch, as the whole company, has quite some history. We are in the business for over 140 years, or almost 140 years. And since then, we've grown into a huge company with over 90 billion euros of revenue per year and a profit of 5 billion euros. All in all, we have associates of over 400,000 people working in over 60 countries worldwide. And I think a very exciting feature about Bosch is that we are not in the stock market, but we are a so-called limited liability company. That means we have a Robert Bosch Foundation, which takes a share of our profits and uses them for general purposes, for generous purposes, for example, into education or also in societal benefits projects, which is, I think, really nice. These are the numbers that are for the whole Bosch family, and specifically for MEMS. We have started as one of the pioneers, I would say, for MEMS, because one of my colleagues, Franz Lermer, he's quite famous in the MEMS field because he invented the so-called Bosch process, which some of you know as deep reactive ion etching. This was in the, I guess, 1992. And a few years later, already in 1995, we started with the first production of MEMS. This was, I would say, far before my time at Bosch, of course, but it's interesting to see that we have such a history there. Up to now, we have produced over 20 billion MEMS sensors, which is a huge amount, and we are holding, I guess, most of the patents, which is over 1,000 patents right now. An interesting feature about Bosch is that in MEMS, we are producing everything in-house. So from the development to the production to the delivery, everything is done in-house in our fabs and also in our development departments. Looking at the locations, our headquarters is located in Reutlingen, Germany. And this is also where I am situated. But we have a lot of other facilities and departments all over the globe. If you're looking into other opportunities, there are always some chances up for you there. Okay. After this short introduction, I want to dig deeper into the solution that the MEMS from Bosch are offering. Looking at the Bosch MEMS, we are part of the semiconductor product portfolio at Bosch. So we are in the MEMS business, but we also are closely related to our MEMS foundry services. And with this, we offer external companies and also especially startups the opportunity to produce their ideas at our production facilities. So you can come directly to us, talk to our guys at the foundry services and see if we can develop also, for example, a specific process for you that enables your product. And with the experience that we have over the last decades, we have quite some knowledge about how to do that. In addition, we also have the colleagues working in integrated circuits. These are, for example, in electronic control units. For example, if you want to control a radar in a car. And also we are deep into power semiconductors, which is quite an important and growing field, especially for the electrification, where they are, for example, used in inverters for batteries. What all of these applications have in common is that the main feature is the law of scaling. And the reason is the economy and the consumers only accept certain new innovations if, of course, the price tag is right. And this is something which I learned when I came from academia to Bosch, because at my university, I had a facility production that there was maybe one working product or one working specimen, and this was like a golden device, and there was the only unique one in the world. And now if I look and hold a wafer, like 200 millimeter wafer in my hand, it's almost up to 20,000 microchips and all working the same on one single wafer. So the act of scaling is what makes the MEMS profitable, because only then you can afford something like $1 billion fab and produce something like in there. This is really important to know. And when you look at all the different applications, we can categorize them into different sectors and different pillars. I won't go into details in all the different activities down here, but for pillar 1 and pillar 2, I have some slides in the follow-up. This is why I want to specifically focus on here pillar 3 and 4 on the slide. Pillar 3 is, I think, a very interesting part, because in the future, or also right now, you can see it's all going into individualization. So individualized healthcare. For example, if you have a sensor which monitors your blood pressure, for example, or even if you have, for example, new running shoes and you have an accelerometer, you can directly detect if, for example, the running shoes have a different effect on your style of running, and you can compare this. So this individualization is, I think, quite important also as a new line of products. Additionally, in industry, this is also very important to have MEMS sensors, because automation, the industry 4.0 and so on, can only work if you are sensing your environment and sensing the world. So let's now dig deeper into pillar 1, the automotive section. If you look in a typical car, there are at least 20 MEMS sensors in every car. And a lot of them are installed there for safety, but also for advanced driver assistance functions. For example, take the classical airbag. Every car has at least 3 or 4 airbags, front airbag, side airbag, and so on. And all of these airbags are controlled, monitored, and triggered by MEMS sensors. For example, an accelerometer that detects if you have a crash, or a pressure sensor in, for example, the front bumper to see if you hit a pedestrian, to stop the car. These are all safety functions enabled by MEMS. But not only the safety functions are there for the MEMS, but also, for example, comfort functions. If you have, for example, microphones or accelerometers that detect the noise coming from the road, you can cancel out this noise and you can have a much quieter and smoother experience in your car. And also some other functions, for example, like navigation. If you drive into a tunnel, you lose your GPS signal, but the inertial measurement unit in your navigation system still knows that you're going along a trajectory and, for example, making a curve in one direction. And this is quite important that we have all these MEMS sensors in a car and for the different functions. And around every third sensor is coming directly from Bosch. So what are the key requirements that these automotive sensors have? One main thing that they have in common is a lot of them are safety relevant. So you need high reliability, high quality. And this is quite important because in a car, there can be quite some harsh conditions. Depending on where the sensors are located, they can experience temperatures from -40 to +120 degrees. You can imagine, for example, the camera at the top, if the sun is burning down on your car, this is quite some extreme conditions. And all these sensors have to work under all these conditions, under humidity, under dust, and so on. This makes the development of such sensors in an automotive regime very challenging. Also, these sensors have to live for at least 15 years under such conditions. And this is important. For example, if you look at pictures that are up here, there are very, very harsh conditions, and you still have to function afterwards. Okay, the next big pillar that we have is consumer sensors. And consumers is a really, really big field, because if you look at MEMS consumer sensors, they can let's say, be everywhere. Typically, for example, in a smartphone, you have, I don't know, let's say around 7 or 8 at least MEMS sensors in there. You have, for example, the accelerometers that help you when you switch your orientation of your smartphone. It automatically detects this and rotates your monitor, your screen. Or, for example, if you take a picture, all your shaking and vibration of your hands can be stabilized with a camera stabilization, also utilizing MEMS. In addition, there are a lot of microphones in there, and these microphones help you also distinguishing the noise from the environment from you talking into the phone. And this is just one example. And a lot of these MEMS sensors are also in, for example, hearables, in wearables, and also in augmented reality applications. They can monitor, for example, automatically your steps you are taking, but also something like your vital functions if you have, for example, a smartwatch. And this is all possible with MEMS. They are also in different applications, like, for example, in laptops. If you drop your laptop, for example, the hard drive is protected by an accelerometer because it detects the fall and switches off the hard drive so that your hard drive is not damaged when the laptop falls down on the floor. And as you can see, this consumer market is huge and it's still growing. If you look at, for example, in directions of smart home, MEMS sensors can detect if your window is open, or it can detect if there are some dangerous gases in your house and warn you about this. And, for example, automatically switch on the climate control if there's something going on. So this is very interesting and also a lot of applications. And a very recent development, which I find extremely exciting, is the size of these sensors. Because, I mean, you know, MEMS sensors are typically very small, but they can be even chip scale small. So we have this new accelerometer, which is the 3-axis accelerometer from Bosch Sensotech. And it is so tiny that you can barely see it. This is sitting on a match, and if you occasionally drop some of these, you have really difficulty finding them again on the floor because they are so tiny. And these small sensors allow for completely new applications. I mean, you can already imagine they are in your earpods, they are in your smartwatch, but this can even enable another function that you can somehow see here. You can put them, for example, into a ring, and then this enables, of course, much more new functionalities that you can, for example, detect what the difference between your angles of arms to your ears and so on are, and opens much more new possibilities, which is quite interesting to see and can be possible with very small sensors with also low power consumption. So what are the requirements for consumer sensors in comparison to automotive? Automotive, as I said, is very focused on quality and on safety. For consumers, it's a little bit different because it is not so important that your sensor is always 100% correct, because in some cases it is okay to have a sensor which is, for example, lower in power consumption and lower in cost rather than being perfect in all the time. Nevertheless, performance plays a huge role, and also robustness, because if you have, for example, a smartwatch and you go from a climatized room out to the open where it's a lot of humidity, your sensor still have to work. So robustness is also a very important feature. Also, these sensors get smarter and smarter every day, and a lot of these functions are already integrated into the small sensor itself. For example, step counter, because step counting can be already done on the small sensor. Then it is able to reduce the power consumption of the whole device, making it much longer in lifetime. And now, in my last section, that I want to tackle some of the challenges that we face with MEMS, and I especially like this picture here because it's interesting that we even have a Bosch Sensotech sensor which is on Mars, and this one is in, for example, the small drone in the Ingenuity rover, and it has flown a lot of flights already, and it's quite nice to see that even these sensors work in such harsh environments, such as the Mars or other planets. So as you have seen, MEMS have been in the economy for quite some time now. We started in the automotive industry, then later came the consumer industry. And now it's growing in the health and in the industry applications exactly. And why are we still searching on MEMS, and what is the future for MEMS? And the idea is besides that I showed you these new applications that are coming in, that there are also challenges with the existing ones. I always say, I like this quote, when you try to develop a sensor, it's quite easy to make it sense something. For example, if I want to develop an accelerometer, you can design it quite easily and you can sense acceleration. This is quite nice. But the real challenge is that you can only sense the accelerometer and nothing else, because typically a sensor, the first time, it measures also temperature, it measures stress, humidity, and so on. And this is the real challenge, that a sensor only is sensing this dedicated quantity that it is designed to do. And this is also a lot of challenges that we face currently to make the sensors even better. And advances can be done in all the fields. We have so many different domains in semiconductors, and especially MEMS. You can, for example, improve the processes to make the sensors even more accurate, that you can always produce the very, very same sensor. Or you can even develop completely new processes that, for example, incorporate new materials like piezoelectrics or some other stuff. Then there's a lot of advances in design and simulation, because it takes quite some time as well as money to produce low quantities of sensors. And in the development phase, you only have low quantities of sensors. This is why it's very important to have a very strong simulation environment to early predict of what the sensor will be and how it will perform. This is a very important feature to also go in design. And also in the other fields like packaging, there is a lot of stuff to do to make it more robust against all the environmental effects like dust or humidity, temperature, and so on. This is an important field. In terms of testing, there's also quite a lot of ideas going on. For example, that a sensor can be done with algorithms and integrated so that it is able to have a self-calibration, that you don't need to calibrate it once and then it drifts away over time, but it has the ability to self-calibrate and reiterate its accuracy. This is a really interesting point, which is also what we are investigating. And as I started as a designer at Bosch in my early career, this is also a slide that I like, because this shows also how, for example, the size of a gyroscope changed over the years. So we started with this in 2012, and over a few years, we came to a smaller size, which is 3 times smaller, and you say, well, this is nice. But the funny thing is, even with a smaller size, the performance increased. Typically, you always say, shrinking something down, you get lower capacitances and so on, it gets harder. But here, we even increase not only the performance, the sensing capability, but also the robustness. And this is also an interesting thing, because we are semiconductors, we're dealing with Moore's law here. We are in full effect. We are growing exponentially if you combine all the different performance features that we typically have in a MEMS sensor. So really exciting stuff. And at the edge of what is physically possible. This is where we always are. So why do I think MEMS is a highly exciting field? I think it is especially exciting because you have to have a lot of domains working together. You can specialize in one field, but to really produce a MEMS sensor, to develop it, you need so many expertises. We saw just before, we saw the MEMS design, but you can also go into ASIC design. You can go into, for example, microcontroller integration. We always need project managements to bump up the huge projects with the different domains and so on. We have system architecture, where I'm coming from, combining all the different domains together. And we can go into processes, into material sciences, and also into measurement technology, which is also a very growing field. And in the last years, also coming up with advances in AI and also data science, we develop new algorithms for the sensor so that the performance and the functions of a sensor increase over time. This is also very interesting. So let me come to a conclusion. As you have seen, Bosch is one of the largest MEMS suppliers in the world. We have an extremely broad portfolio of different sensors, and it's still a growing field with lots of new opportunities, lots of new applications that are opened up. I think it's a very interesting field for technology, because there are so many domains and so complex tasks that are to be tackled with, that it's really a fun topic if you are a scientist or an engineer to really dig into these topics. And we see that these sensors become smarter and smarter every day. They have new functionalities. They can increase in their capabilities to perform even more complicated tasks. And this is why I want to encourage you. Please pursue a career in MEMS sensors. It's a very exciting field. And if you are interested, you can always contact me or our HR department. You can contact me via email, for example, or via LinkedIn. I'm happy to answer your questions. And with that, I would like to conclude and acknowledge all the different funding groups also that made this possible. Thank you very much.
Thank you, Matthias. That was amazing. We went into a fantasy world, literally seeing all the gadgets and all the automobile sensors built into them. It was great. We'll take the questions at the end of both the talks, and both of you can answer accordingly. But the future looks bright from industry perspective, and that's what we wanted to show to all the audience that we have here. So thank you, Matthias. And the next speaker that we have here is Dr. Geronimo. He is from Texas Instruments in Kilby Labs in the US, but he is also a visiting lecturer at the UC Berkeley in the US again. And Geronimo is actually an expert in RF MEMS. And if we are all able to really have some great communication going on, even looking at the screen now, talking over our mobile, all that is because there is a lot of RF MEMS that has gone into these communication equipment and communication lines. And Geronimo is one expert in that. So he's going to speak on RF MEMS technologies in industry. Thank you, Geronimo, for accepting this invitation, and you can go from here.
Thank you, Veda, for the kind words. Yeah, so yes, my name is Geronimo Segovia Fernandez. I'm a PhD in electrical and computer engineering, and as Veda mentioned, I work at Texas Instruments Kilby Labs as an R&D engineer, but I'm also visiting lecturer at University of California, Berkeley. So today I'm going to talk about RF MEMS technologies in industry. Okay, so this is the content of my talk. So first, I'm going to give you a forecast of the MEMS market as well as the top MEMS companies. One of the main applications for RF MEMS is smartphones and wearables. So I'm going to show you the inside of these devices and highlight where the RF MEMS, where we can find the RF MEMS devices there. Three types of RF MEMS: filters, oscillators, or timing devices, and switches. And then I'm going to give you some details about each of these technologies. Okay, so this is the the MEMS market forecast. So here you can see the number of 1 million units that are sold a year. So you can see that in 2018, the number of 1 million units that were sold by industry was 20,000. And that number is expected to duplicate in the 2028, so just in 10 years. And actually a big portion of this number of sold units, it comes from RF MEMS. So you can see the dark red color here. It's actually the number of RF MEMS units that are sold per year. And then also MEMS timing in this graph is separated. That's the clear red color here. But altogether, it's about 70% of the entire MEMS market. So you can see it's a big amount. In terms of US dollar revenue, in 2022, the total revenue, it was about 14.5 billion US dollars. In just 6 years, in 2028, it's expected to go to 20 billion. And that adds to a compound annual growth rate of 5%. And then if we look into the market segments that experience the largest increase, one is MEMS timing, that, as I mentioned, I include within RF MEMS. That's a 20% growth. And then the second largest growth in this MEMS market is actually RF MEMS, and that's a 6% growth. So you can see there's a very big opportunity for RF MEMS in this market. Now, if we break down the revenue in US dollar millions into companies, we can see Robert Bosch is actually the first one, the we heard before, they have a lot of MEMS products, so they have a big sales here. Actually, let me also clarify that these revenues for these companies, some of these companies, they sell other products that are not related to MEMS, but this revenue is only coming from the MEMS market for these companies, okay? So now, if we look into the companies that they sell RF MEMS, so the first ones that comes are the ones that sell filters. So big example is a Broadcom or Avago. Then we have Qualcomm, Qorvo, Murata, and Skyworks. You can see this account like a leading companies here. Then in terms of oscillators or timing, we have Texas Instruments and SiTime. Although here, let me clarify, Texas Instruments in this revenue also includes digital micrometers. Okay, so it's not only timing. And then finally, we have switches. The big two companies that sell switches are Qorvo and Analog Devices here. Okay, but where can we find RF MEMS? So one of the big customers for RF MEMS is smartphones and wearables. So for example, we can look inside the iPhone 12 RF front end, and there is one module close to the antenna. It's actually the RF transceiver. And in this case, this is a module fabricated by Avago or Broadcom. And inside the module, all integrated, it contains 4 power amplifiers, 18 MEMS filters. Each of these MEMS filters, as I will describe later, contains many MEMS resonators. We have switches. These switches are not, in this case, not MEMS switches, but I expect in the future they will become MEMS, RFIC, and also a matching die. Inside the Apple Watch, we actually identify a filter and also a reference or oscillator from SiTime. Okay, so why do we use RF MEMS filters? Well, the reason for that is because of the crowded frequency spectrum. So in telecommunication, we have to emit and receive at a specific bands dictated by the governments and their frequency agencies. So for example, in the case of the personal communication service band, we can see that the uplink and the downlink, they are very close to each other with just 20 megahertz of margin. So in order to separate these two bands, you need to have 2 filters with very high roll-off. So traditionally, these filters were made of surface acoustic wave devices, okay, that are made of a piezoelectric substrate. But now, because of the benefit in terms of a roll-off, as you can see in this graph, and better insertion loss, these soft filters have been replaced by BAW filters, which are basically specific devices that are made of a piezoelectric layer that is separated from the substrate. Okay, so, and there are different, the way that you configure these filters can differ from the application. So we can have electrically coupled resonators. When we have several resonators in series that are coupled just by the electric capacitance. In this case, you are targeting very narrow channels or frequency bands. Now you want to target wider frequency bands. You either use a ladder configuration or a lattice configuration in which you combine series and shunt resonators. And in this case, you actually, if you design the resonance frequency of the series different from the shunt resonators, you can actually increase the bandwidth. And then if you use the lattice configuration, you can have a higher radiation, but poorer roll-off. And then in terms of, because of this market is very attractive, there are many companies that are looking to take a role or take a portion of that market. And they all have their BAW technologies with different fabrication specs, right? So the first one was Avago or Broadcom that came out with the film bull acoustic resonator. Here you can see on the left, It's just a released piezoelectric layer sandwiched by 2 electrodes. But then other companies came into the market and they developed different ways of how to isolate the piezoelectric layer from the substrate. And for example, they invented the solid mounted resonator, in which instead of releasing the piezoelectric layer, now you attach it to a acoustic Bragg mirror, similar to optics. But acoustic Bragg mirror actually isolating acoustically the piezoelectric from the substrate. So, so there are different ways of constructing these both devices. Okay, let me switch gears here. Now I'm going to talk about oscillators. So this is the timing market. So basically, an oscillator is just a frequency source. In the ideal case, you want to have a frequency outcome that is stable over time. So basically, the frequency doesn't change over time. So if you plot the phase over time, you have a straight line, okay, proportional to time. However, in reality, the oscillators, they drift over time. So the frequency becomes unstable. And you can see how the frequency changes over time. If you plot the phase over time, you have a deviation from the straight line, okay? So you want to minimize this deviation, because by having this instability, you actually lose accuracy of your clock, okay? So your clock doesn't provide the right frequency. So in the short term, when you're looking at the very short term for the stability below 1 second, the way that this phase noise is plotted is in the frequency spectrum. You just plot a phase spectral noise density over offset frequency. And actually, traditionally, these devices were made of quartz crystals, but now MEMS oscillators actually improve the phase noise, especially in the jitter frequencies, which comes from 12 kilohertz to 20 megahertz. So if you integrate the noise here, you actually get a much smaller RMS jitter that you can get with quartz. So that was one of the main difference for MEMS oscillator. It took several years to achieve this better performance, but now the MEMS oscillator have outperformed quartz. Another aspect in which MEMS oscillators are becoming better than quartz is in long-term stability, as I mentioned, above 1 second. So the two main factors for long-term stability are edging and temperature drift. So in terms of edging, you can actually extrapolate the frequency stability to 1 year or 10 years. And actually, in this case, SiTime improves the performance of quartz in these two cases, as well as in temperature drift. Because over temperature, these technologies, they need to also be stable. So by doing compensation using like doping the materials or adding new materials, you can actually go from the uncompensated MEMS temperature drift to a much more controlled temperature drift that in some cases it actually improves the intrinsic temperature drift of the quartz crystal. So that's the reason why now MEMS oscillators have started to replace quartz crystals in the timing application. And finally, I'm going to talk about the later comer to the RF MEMS market, which is the MEMS switch. So MEMS switches have been theorized and explored for decades in academia, but not until recently they have been more introduced in industry. So finally, companies are finding like good applications and the right performance for this application. So from the fundamental point of view, RF MEMS switch is just as basically a source, a drain, and then you have a gate in which you apply a voltage. And this source and drain are connected by either a cantilever beam or a clamp beam. So the goal is that once you achieve a voltage difference between the beam and the gate that is above the pulling voltage, actually that beam will snap into the drain and then the current will flow. So from the fabrication point of view, you have 4 main steps. So you use a high resistivity silicon wafer to reduce the parasitics. Then you create the dielectric layer and interconnect. And then after, you are gonna deposit and pattern the cantilever beam. So you use a metal for that, low resistivity metal. So a good example is gold. But for the tip, normally you use another material that is harder than gold, because these cantilever beams, they need to support billions of cycles for reliability. And finally, you encapsulate the whole beam with a silicon cap to protect it from the package. So many applications for RF MEMS switches. So from test and measurement equipment to wireless communication, radar, aerospace and defense and medical devices. The advantage of this RF MEMS switch is the low power and integration. So basically in any application that you require low power and integration, I think RF MEMS switch is the perfect candidate. So here on the right, I just showed a very a specific application that actually has been used in telecommunications, which is the tunable transceiver. So basically, the problem with the standard transceiver is that the antenna will need to match to the components that you have in the front end. But because these antennas are becoming smaller, and you are basically changing the equivalent impedance of the antenna. So to make this antenna to be to match with the transceiver, you actually use a switch that can adapt to the inductance or capacitance. So then you can match the antenna to the transceiver. And actually, this company, Cavendish, was acquired by Qorvo a few years back because of this invention. And then if you compare RF MEMS switches with electromechanical relays or solid states, so especially you compare with electromechanical relays, RF MEMS switches, they achieve a higher linearity, lower power consumption, longer life of switching cycles, faster switching speed, and then in terms of size, as you can see below, it's much smaller because now these switches are integrated in a SMT package. On the table on the right, they also compare MEMS switch with the solid state like transistor switch. And one of the big advantage is insertion loss. Okay, so the MEMS switch has much smaller insertion loss because you can actually, you know, as we are using a very low resistivity material beam, you can actually reduce the amount of losses that you have in the transmission band. So finally, I want to give you my remarks. So as I mentioned at the beginning, the MEMS market is increasing in volume. So it will double in the next 10 years, and it will provide a compound annual growth rate of 5%. 4 out of the top 6 MEMS companies sell RF MEMS in the form of filters, oscillators, or switches. And smartphones and wearables contain many of these technologies. In telecommunication, filters require low insertion loss and steep roll-offs. So under these conditions, both prove to outperform Thor resonators. In 4G and 5G markets, many companies are competing. And to compete, they have different BAW technology with their own patents and IPs. Stability is key to achieve high accuracy for timing. So in this context, MEMS oscillators have proved to outperform quartz crystals in terms of jitter, temperature, and edging. And then finally, I talk about RF MEMS switches, which are a later comer to the market. but they find their fit in tunable transceiver and low power applications. And in comparison to electromechanical relays, RF MEMS switches show higher linearity, less power consumption, longer life, faster switching, and smaller size. Okay, so with this, I end up my presentation. So thank you. A little bit of promotion of the Sensors Council you can find here. And also, you have any questions, you can write me to this email address, and I will try to answer them in a prompt manner. Thank you so much.
Thank you. Thank you so much, Geronimo. It was wonderful to see the applications you have shown in RF MEMS, and truly you're an expert. But what came out from your talk as well as from Matthias' talk is something on the smartphone. So Matthias talked about MEMS inertial sensors and other kind of pressure sensors that go into a smartphone. And you said about taking those signals and doing the filter operations using the RF MEMS for communication purpose in smartphone. So in true sense, if everyone and anyone who is using a smartphone, you are using MEMS technology. That's the big take from both the talks. Not just that, even if you talk about an automobile, there are a lot of inertial sensors and other MEMS sensors, but then there is GPS and other communication systems which goes into an automobile, and RF MEMS comes into picture there as well. So it's a lot of things that come in. People don't understand they are using MEMS every day, but it is by default there in their lives. So thank you both of you, Matthias and Geronimo, for this wonderful talk. And we'll take questions now. You can give questions on both the talks that both the speakers have given, but you can also ask me about the MEMS training and the design submission, the groups, and other things. So any kind of questions, the audience, please put it in the chat box and we'll take it one by one. So first one is already there for you, Geronimo. If you can see the chat box, what is the application of RF MEMS in healthcare? You want to take that?
Yeah, so I think for healthcare, if you refer to MEMS switches, I think this is like a newcomer. So it still needs to be more explored, but basically the goal is to apply them to any kind of technology that require low power consumption and a high level of integration. So I don't know, in healthcare, maybe for operation, robots, I mean, now it's like big companies, they are exploring using robots for surgeries and interventions. So whenever you need to use, like integrate these switches in this robot, I think there will be application, and also for communication. In telecommunication, any type of device that you need to communicate with, it most likely will contain RF MEMS in the form of BAW filters. So yeah, I would say that, yeah, it's a very pervasive technology.
Thank you. Second one, Matthias, that's for you. If you can see that, how would you predict the future of MEMS speakers? Has Bosch done any research or development on this field?
Yeah, thank you. Very good question. Yes, indeed, Bosch is active in all the different fields of pre-development and research, and we are collaborating with lots of institutions and research institutes, also, for example, with Tyndall. And MEMS speakers particularly, yes, in the last years, we also acquired via our partner company Bosch Sensor Tech, another company which is called Arioso, who is researching and developing MEMS speakers. And this is also one of the fields that we are very interested in.
Okay, thank you. That's great. Next one again for Geronimo. What is the specific application of RF MEMS switches for Bluetooth and Wi-Fi modules?
Yeah, so as I mentioned before in one of the slides, what I see is like in RF transceivers, you actually need to switch between different bands, right? So you have a unique antenna, and then you have different bands separated by filters. You need to switch and connect the antenna to either the transmitter or the receiver, right? But at the same time, the antennas are becoming smaller, right? So by making the antenna smaller, now the antenna it's not 50 ohms anymore. So it changed the impedance. So the innovation here is that not only you provide the switching between transmission and receiving, but also you can match the equivalent impedance of your antenna by also combining inductors and capacitors that you can also switch, and you can apply different values. So I think that's where the main innovation and the contribution of RF MEMS switch is in the communication market.
Okay, perfect. Thank you. Then the next one is also for you. What process is best for MEMS oscillators? Is it like soy or what is it?
Yeah, so I guess there are different ways of make the MEMS oscillator. So you can use a silicon-based capacitive MEMS oscillator, like SiTime does, for example, or you can use a piezoelectric MEMS-based oscillator, like, for example, the one from Texas Instruments. So it depends on the type of oscillator that you want to use. You will use a very different fabrication requirement. So it also depends on the frequency specs that you are trying to target. Like normally for silicon-based oscillator, you are targeting lower frequencies in the order of tens of hundreds of megahertz. In the case of piezoelectric MEMS oscillator, you are looking for gigahertz frequency. So also the final application dictates the technology and the type of process you want to use.
Thank you. That's perfect. Vishaka asked me, what about the previous talks link? So all the talks, and including this webinar, will be available on the IEEE Sensors Council YouTube channel. You can always go to the YouTube channel and find the previous webinar links. The next one, Matthias, is for you. Bosch BMI gyroscope is 2-axis or 3-axis, and which process is used for it? Any info is available.
Mm-hmm. So all the consumer sensors, gyroscopes and accelerometers are always 3-axis. This is required because, I mean, a smartphone can rotate in any direction, so you always need the 3-axis. For automotive, for a longer time, it has been not all the axes, because typically a car doesn't flip over too often. And when it does, I mean, you have the right sensors to detect this and protect this. But all the Bosch sensor tag applications are always 3-axis. And in kind of process, as said, we are using all the in-house processes, and we use for all the inertial sensors a multi-layer process where we have different layers for example, electrodes, but also moving layers, which partially also are connected or insulated, depending on what you want to do. And with that, we can achieve quite high performance, because we can, for example, stack the electrodes so that we can have differentials even out of plane, which is, I guess, also quite unique as a process.
Yeah, thank you. Next one, Geronimo, that is for you. In theory, can MEMS timing oscillators have TCF values better than PPM, like parts per trillion? You want to take that?
Yes, sure. Yes, but the intrinsic TCF or of the MEMS oscillator without doing anything is in the order of 100 or 1,000 of ppm. But then to achieve this kind of low TCF, you need to compensate your material using, for example, the case of a piezoelectric MEMS oscillator. You use silicon dioxide with a different or opposite TCF, or in the case of a silicon-based oscillator, you doped the silicon. So you are able to reduce this intrinsic TCF to the order of tens of ppm, but then afterwards you do electronic compensation with temperature sensor, everything integrated. So then you are able to go down below ppm. And if you want to go even better, you can ovenize your oscillator so you maintain the temperature all the time. So then although the ambient temperature is changing, you are kind of like controlling the temperature of your sensor. So so anyway, there are many tricks you can use to make this TCF, the actual TCF for your oscillator, to be in the order of parts per billion, or I think I have also seen parts per trillion.
Okay, thank you. The next one is also for you, Geronimo. Highlight on the fabrication challenges of polymeric MEMS versus silicon MEMS.
Okay, this is a tough question. I don't have experience with polymeric MEMS, but I would say that perhaps it's more difficult to control the quality of the polymer compared to silicon MEMS, in which like the fabrication steps are better defined and the equipment works with a more in a more specific way. So probably controlling and reliability, I would bet, are easier to achieve for silicon MEMS.
I agree, because it's CMOS compatible, so many processes are optimized when it comes to silicon MEMS. Polymeric MEMS is much cheaper because it doesn't need like the real clean room environment, and it could be a little cost effective, but it's not optimized. So there's a lot of research going on polymeric MEMS as well. But silicon MEMS won't get erased. It will remain because it is very much optimized and it will remain in the market. Matthias, you want to comment something on that?
I think I want to also add that, I also want to add very quickly that in industry, reliability, also Matthias mentioned before, reliability is very important. When you sell your product, it needs to be very reliable. It needs to work the same over time. So you need to achieve a technology that doesn't drift or change over time as much. So that's a key.
Yeah, totally agree. So for timing devices, I would say monosilicon is the way to go because it's much better controlled. But as you said, if you go into price, of course, polysilicon can be much easier and then much larger quantities produced depending on that. But for timing, I would totally agree.
Yeah, thank you. Geronimo, there's one more for you now. When we say MEMS oscillator, are we only talking about resonator made in MEMS die and electronics made in CMOS, like CMOS MEMS integration, or is it totally MEMS giving out frequency?
No, in this case, it's a MEMS resonator fabricated in a separate process, and they're wire bonded or maybe flip chip bonded to the CMOS circuit, and all of that encapsulated. That would be the final MEMS oscillator.
Okay. So my question, again, I have a question in the same lines for both of you, in fact. When we talk of MEMS, whether it is inertial sensors or let's say a resonator, we always can say that these sensors are like the arms and limbs, but then you need a brain for the whole system to work. So there is a system development that goes with MEMS, and you need to integrate electronics. And how challenging is that for a MEMS engineer to look at system integration, bringing in the electronics and making a product, especially from industry perspective? You need to have a different group doing that who have different expertise, but you need to have a common dialogue. So how challenging can that be for a MEMS engineer?
Yep. So maybe I take over. So from the point of, if you look at the bare dies, so the MEMS die in itself, the mechanical, electromechanical part, this is typically done by designers and process engineers. But of course, as a system architect, you need to then combine it with the ASIC, which is the electronics directly reading out the raw signals. And there you also have the separation into front end, which directly controls the voltages, the frequencies, and so on to directly drive and sense what the MEMS bare die is doing. And this is already quite challenging because, I mean, as said before, sensing is easy, but distinguishing from all the dirty signals is the hard part. And there you need to have a lot of interplay between the MEMS and the ASIC designer in terms of system architecture to get the best out of it. If you even think one step ahead, if you have the MEMS and the ASIC, this is just the raw signal coming out. And then if you want to further develop it, doing algorithms, something like step counting, or even more fancy application with timing, for example, to external with APIs that directly connect to, for example, a camera and have a timing device there, then it gets even more challenges. And the interesting thing is that all these domains have to work together in some sense, and you need to structure it very well, which is, I guess, one of the key challenges of semiconductors, because so many people are deep into their one field, but you have to have the broad view to connect, and there is the real value coming out.
Exactly. So what I want to tell to all these people who will be doing design submission next year, right? When you're trying to do some design, make sure that your device is packageable. And you should also think about how to test it. Most of the time, what MEMS engineers do a fault is don't think of packaging because they don't looking at system level application of it. And they don't understand how even the testing of those devices can be. Even they don't make the pad sizes in such a fashion that you can package it or even probe it to do a wafer level testing. So when you're trying to design and put in a mask for fabrication, make sure that you leave the scope for packaging it and taking it to system level. And that's very important from MEMS point of view, because MEMS device by itself cannot do everything and anything. It needs to be packaged and integrated finally to make a product. So that's something to be kept in mind and something that we always overlook when we are designing. And we are only bothered about design and simulation, but we don't look at the real product at the end. And since all of you who are
and actually companies, I want to also add that companies are looking for expertise in package design and engineering. So
yes,
like that's something kind of like companies are, because most of the cost of the MEMS product doesn't come from the MEMS die or the CMOS. It comes from the either the packaging or the test. So the package is very important. So companies, they want to reduce and also because it affects performance, you need to have a very good design of your package.
Yes. And actually, keeping that in mind is our last webinar in this series, which is going to happen on December 16th. And it will be on packaging and testing of MEMS devices. So we want to conclude by telling you exactly how your designs should look and how it can be taken one step further towards packaging and looking at system integration. So I request all the participants today to look out for the calendar invitation, which I'll send out very shortly. It is on December 16th at Irish time, 3 p.m., which is 1 hour earlier than what we started today. And you will be looking at and hearing experts talking about packaging and testing, because the devices that finally get fabricated need to be tested, need to be packaged. So don't miss out on that webinar. And since we don't have any more questions, I want to thank both of you, Matthias and Geronimo, for this wonderful talk. You took us to a different world. It was quite mesmerizing. And we look forward to having your mentorship when the design submissions happen next year. And hopefully you'll get many good skilled people coming out of this whole activity. Thank you once again, both of you, and wishing all the other people great time designing MEMS devices. And if you have any doubts anytime, please do feel free to contact me. Thank you.
Thank you very much for having us.